My name's David Singleton, and my day job is that I am an engineering director at Google here in London. But I'm not here to talk about that today. What I'm here to talk about is a fun weekend and evening project, which was that I built a neural network controlled, self-driving, radio controlled car. So it would have been more fun if it was a self-driving actual car, but some practical limitations meant that it was not exactly like that. You can't really read this washed out text at the bottom, but if you want to follow me on Twitter, I am DPS, and there's another link to my blog at the end. Cool. So this is really the story of a hack that involves using really cheap mass-produced hardware and also pretty amazing computing power that we all have in our MacBook Airs and whatever computer you have on your desk today. So I'm going to tell you the story of the hack that I did, but the themes I'd like you to take away are through open source hardware and the actual value that you can get in these really cheap mass-produced devices. You can do some pretty amazing stuff. So the sky's the limit, and hopefully this will inspire you to do something similar yourself. So here's how I got inspired. I was actually writing another talk, a talk about the relentless innovation that's gone on in compute power with the advance of Moore's law over the decades. And this was the first slide of that talk. It's a picture I took at the Computer History Museum, and you can see all of these processors. So really pretty amazing how much more compute power there is in this device than the supercomputers of just maybe a couple decades ago. At the same time, as I'm sure some people in the room will have done, I decided to start taking the Stanford online machine learning course to sort of refresh my knowledge of machine learning. So that was pretty cool and got me quite excited about these two things together. So how many people in the room did also try out the Stanford machine learning course? Okay, awesome. So a few of us. It was a lot of fun. If you haven't done it already, I recommend trying it out the next time they open it up. I'll put the links up at the end. So on that course, they had this interesting module about neural networks. And neural networks are an interesting machine learning technique. They're kind of modeled on the human brain. And they were super popular in the late 80s and the early 90s. And then folks started to realize that they couldn't really do anything particularly interesting with them, so they kind of died a death and other techniques took over. But they've come back into fashion in the last couple of years as this amazing amount of compute power has started to mean you can do pretty serious stuff with neural networks. And on the Stanford course, they talk about this project. So this is a kind of military vehicle called Alvin, which stands for Autonomous Land Vehicle in a Neural Network, which was able to drive itself around the roads near Carnegie Mellon University back in the kind of mid-90s. And they show a video of this, and here's how it works. So this is a computer display inside the vehicle. They have a picture that's being taken by a camera mounted on Alvin every 2 seconds. And this picture is 30 pixels tall by 32 pixels wide. And you probably can't tell, but that is actually the road in front of the vehicle. And it's continuously passing those images through to a neural network, and the neural network is figuring out how to drive the car. And the way that it figures out how to drive the car is that they've actually done the same thing. They've driven a whole bunch of different roads, but with a human driver, but still capturing these images every 2 seconds. And by learning on the data when a human was driving, then the computer running the neural network can take over and actually very successfully drive the car. And it's very exciting. In the video, they have a car leave a little single track road and merge onto a highway. And it would be pretty scary to be one of the cars anywhere nearby it, given this was so primitive, but it works and it was very exciting. So that got me to thinking, well, I'd like to build something similar myself. So I knew I needed a few things to build a self-driving car, and probably the most obvious is I needed a car. So I actually opened up the Argos website, and I found the cheapest car you can possibly buy on Argos. That's this one. It's a Nissan GTR, ish. It costs about £7, and it comes with the car. It lights up when you drive it around. It's very fun, and a little remote control. So that's the car. I also figured that I would probably need some way to take those images. So what bit of cheap hardware did I have that can take images? Well, I had my old mobile phone, which is an Android phone, And I thought, well, that seems like a good place to start in order to get images. And it would be really cool if I could have managed to just have the phone run all the software on it and control the car directly. And there actually are some interesting ways that you can connect Android phones to hardware devices. This is an Android ADK board. I'll talk more about what that means in a little bit. It would have been really cool if I could have put this inside the car and had the phone mounted to it. But unfortunately, with this technology today, you also need to provide enough power to power the phone through this board. And when I tried to get that all working on this 7-pound device, it was clearly not going to work. It wasn't going to be able to drive it around. It was going to be too heavy. So back to planning how to get the kind of whole system working, I decided to try something that might seem a little bit Heath Robinson, but I actually think it's quite a powerful technique in general, which is that I figured I could just run stuff on my desktop or my laptop computer and somehow figure out, I'll talk about how this works in more detail, somehow figure out how to control the car via radio control. And use a Wi-Fi network to actually get data from the phone back to the computer. So this is how the whole thing actually works. There is a phone capturing images, and it's sending those images to the computer in a stream. The computer is doing some stuff that we'll talk about in a bit, and is connected through an Arduino, which is an open source hardware kit, which we'll talk about in more detail in a second, to the original remote control of the car, which then drives the car. So even though the phone is sitting right on top of the car, it's actually communicating back via the PC. But when I say that this is kind of powerful, it means that all of the tools and software packages that you've been using to develop stuff on your desktop or laptop computer can be applied to these kind of hardware problems, which is a lot of fun. Cool. So let's look at how you can do this hardware hacking, because that's maybe the most challenging bit to anyone who's been used to building software. So what's the anatomy of a really cheap radio-controlled car? And really what I'm talking about is the anatomy of a radio-controlled car controller, because that's the bit that we actually need to figure out how to automate. So inside these controllers is usually a printed circuit board, and the really cheap cars, instead of driving servos that kind of sweep through a range, which you would get in an expensive car, they just have on and off switches, and they either are going forwards, backwards, left, or right. You can't do anything else. You can't be like halfway left or halfway right. So if you rip your bits of plastic off your radio controller, hopefully by doing a bit of Heath Robinson tinkering, you can figure out how it actually works. And so that's what I did here. So I used an extremely cheap multimeter. If you have access to an oscilloscope, that might be even better. I used a cheap multimeter to figure out what the resistance was between various points when I pressed the buttons. And it was a total trial and error mechanism. You can kind of trace out the lines on the circuit board that go from each of the buttons to wherever it seems like they might go. And with a bit of messing around, I actually figured out exactly how the controller worked. And it turns out that when you press each of these buttons, those are the ones for up and down, forward and backward, and left and right, it makes a connection between some pad over here and ground. And so, having figured that out, I needed to build a little circuit which would allow me to simulate a human pressing the buttons. And this is a pretty powerful technique. You can do this with anything. You can do it with a cheap radio-controlled car controller, but you could also get the remote control of any of the devices in your house, rip it apart, figure out how to have a circuit connect the two things that would happen when you press a button, and you can kind of control anything. And since hopefully the devices were cheap in the first place, it doesn't matter too much that they're not very useful for anything else afterwards. Cool, so having figured this all out, I did a bit of soldering, which was fun, and managed to get something working. And the schematics of the little circuit I built are on the website if you want to build it yourself. And then I needed to connect that circuit to a computer. So this is where the open source hardware board, an Arduino board, comes in. How many people have played with Arduino? Okay, actually most of us, cool. Well, for those who haven't, these are pretty inexpensive pieces of kit. They cost about £40. You can get them a little bit cheaper. They come in all sorts of varieties. And this Android ADK board that I showed you a little bit earlier, it is itself an Arduino board. There's a standard spec for how the development environment talks to the boards. and they each have a small AVR microcontroller. This is the microcontroller on the Arduino Uno, which can be programmed via this kind of standard development environment. And this environment makes it really easy to write programs that can read inputs, read serial data from the computer, and also write outputs. So the little program that I had to write is extremely simple. This is a slightly paraphrased version. But when you're writing code for the Arduino, you typically have two parts to your program. You have a setup function. You can see here it looks a little bit like C or Java-like syntax. It's actually neither, but they tell you it's Java. You have a setup function, which runs first. And in that function, you want to kind of configure everything, say which speed your serial port's going to run at, and tell it some pins are going to be output pins. And then it has another function called loop that it just runs over and over and over again and again until you pull the plug. And you can see here that what I'm doing is reading some data from the serial port, so that's going to be connected to the computer, figuring out which bits are set in the byte that it's read from the serial port, and then turning on the pins corresponding to each of the buttons I could have pressed on the controller to make the car go. So again, all of this is available on my website if you want to do it yourself. We can make the electronics a little bit smaller. So instead of keeping the plastics of the remote control around, I ripped the circuit board out, did a bit more soldering. And here you can see on the left, there's an Arduino board. In the middle is a breadboard with my little circuit that pushes the buttons. And on the right here, that is the actual original circuit board that was inside the radio controller. And in fact, all of that stuff is inside this cardboard box that's on the podium here. So putting that all together, I'm now able to drive the car from a computer. And that's what the overall kit looks like. Car, computer, USB cable to give us a serial connection to the device. So we'll come back to this in a second. Next, I want to talk a little bit about neural networks and explain how we could possibly have a neural network drive the car. How many people have implemented a neural network? Wow, that's awesome. So this is a well-informed crowd, in which case you can correct me when I get stuff wrong. So you can't really see the gray connections here, so I'm going to explain, and you can kind of imagine in your mind. So the way a neural network works is, I said it's kind of modeled on how the brain works. So the idea was, in the brain, there seem to be these cells, and they have connections to lots of other cells. And those connections are called neurons, and the actual cells are called brain cells. And a neural network was kind of imagined to be similar. So in a neural network, we have lots of nodes. We have nodes in an input layer, and definitely nodes in an output layer. And then we can have an arbitrary number of what are called hidden layers. These are layers of nodes that do something in the middle of the network, but they're not related to the input or the output. But by figuring out how to connect them in the right way, with the right weights between the nodes, you can actually have the network learn to do something. So what I did in this case was I used what's called a convolution network. A convolution network is something that's typically used in image processing. And what it means is, for each frame of video data that is coming in to this system, there's actually one node for every single pixel in that frame in the input layer. So I was actually capturing images here at 176 by 144 pixels. Sounds like a very arbitrary number, but it's in fact the lowest resolution you can capture images at in Android. And you'll find that across all devices. Still significantly higher resolution than what the Alvin system was using in the 90s. So it turns out that gives you 25,000 units in your input layer, and one special one that just always emits one, which can be used to do interesting things. Then, in this case, I chose to use just one hidden layer. If you do the Stanford course or read any of the books on this, they say, try one layer first, and if that doesn't work, try more. So I tried one layer first. And picking the number of units in the hidden layer is a bit of a black art as well. I think I tried 8 first. It didn't work, so I tried 64, and guess what? It worked. So there's a hidden layer, and then on the output side, we have one node for each of the things that you can do to the car, for each of the buttons that you can press in the car to make it drive around. So there's one for left, one for right, etc. And the way the neural network works is that there are actually connections between every single one of the nodes in the first layer to every single one of the nodes in the next layer, and so on. So there's a connection from every single one of these to every single one of the ones in the output layer. And what each node does is it adds up all the inputs coming from the nodes connected to it, which each have a weight. So it's like a multiplier that means how important is that node to the one that is kind of calculating. It adds them all up. Some of the weights can be negative, and it thresholds them and says, okay, I have to decide if I'm going to output a 1 or a 0, and passes that on to the next layer in the network. That sounds a bit obtuse maybe, but it's actually quite a powerful concept. Because what we then do is we pass this kind of arbitrary ton of junk, a bunch of data. And the data, in this case, is they're frames of video that have been taken while I drove the car around. So like the Alvin system with a human driver, I was the human driver here. And by using those data, we start with a completely randomly initialized set of weights for the whole network. And then in a multi-step process, you look at, okay, if I take those input data and project everything through the network, that's called forward propagation, are any of the answers I've got on the output layer what I was expecting to get based on what the human was doing when they drove the car? And of course, to begin with, the answer is mostly no. But then those errors can be passed back through the system, adjusting some of the weights. And if you repeat that over and over and over and over again, then you can actually learn, the system itself can learn the correct weights for each of the connections in the network to make it actually be able to drive a car just like a human. So I find this pretty astonishing and pretty magical. And let me show you a little bit more. Okay, so first step in this process is actually getting some data to train on. So it needs to be able to have a human drive the car around. So here comes a little demo. And this gray text says here, oh no, I'm a horrible driver. I couldn't drive this car much better than I think a really dumb program could. So this was a lot of the limiting factor. So I wrote a little Java program called driver, which I will start here. Hopefully you can see this. Yeah. Okay, so this is a little Java program. And there's another little Java program in Android Java running on this phone called Neural Network Car. And when I run that, it allows me to connect to an IP address. I'm going to put the IP address of this computer in. And hopefully now you can see an image of all of you coming from the phone. So this is what the car sees. Give it another wave. Hello. So this is what the car sees. And if I put the phone on the car, this is more precisely what the car sees when it's on the ground. And you could imagine if it's actually driving around a track, it might see something. I haven't been able to build a track today because I didn't have time. But if you're driving around a track, it might see something a little bit more like that. So it's just getting a glimmer of some of the white on one side. And what I did was I created a bunch of tracks, and I put this into record mode, so it's saving every single frame coming out of the system. And then I tried to drive the car around, which is what I'm doing now. And as the car drives itself around, you get an idea of what it's seeing. Now, I don't actually have an antenna attached to my radio controller, so the range is very short. But you can see that it's actually able to drive the car around as I drive it. And all of those data are written to disk, along with ones or zeros, depending if I was going left, right, forward, or backward as I drove the car around. So that was the driver program. Later, this program will come back to actually drive the car according to the neural network. So there we've got some training data. What we then do is pass those data into the program that's going to train the neural network. And in the Stanford course, they teach you to implement your own training function using Octave, which is a kind of open source version of MATLAB. And here is a screenshot of Octave running on the data from another run that I did before. And it kind of chugs along for a while. It takes about 15 minutes on that laptop to train a network based on driving around a fairly large track that I'll show you a video of just twice. So it takes about 15 minutes, it chugs along, it goes for about 100 iterations, and in every iteration this cost, which is a kind of total error over all the frames, is going down. And eventually, it manages to come up with a set of weights that, incredibly, can actually drive the car. And here's a visualization of what those actually look like. So what these correspond to, there are 65 of these nodes in the hidden layer. And each one of these images corresponds to one of those nodes. And what I've actually done here is plotted the weights coming in from each of the input layer nodes as if that was a pixel in an image. So here you can see there's some white. That means that the weight coming in for the very first pixel in some particular frame, or any frame in fact, is a high number going to this particular node in the hidden layer. And where it's black, which it is up here, that would be a low number. So this is pretty intriguing. This is completely magic, in fact. This is just numerical optimization. And look at what it's produced. These are like little filters that look like edge detection in the middle distance in various different directions. And I mean, it's impossible to know what this really represents, but numerically, this provides the very best way of driving the car. So that's what the elements in the hidden layer look like. What's quite interesting then is to say, okay, so how can I visualize the next layer? Well, I've done that. I've actually sorted the elements in the hidden layer by the weight that is given to them in terms of whether or not the car should go right. So that looks like this. So if you sort them based on how important they are for steering right, and actually 0 is here. So these ones all contribute negatively to driving right, and unsurprisingly, those are the ones that correspond to driving left if you sort it the other way around. These ones don't really mean very much, and then these ones are very strongly telling the car that it should turn right. And if you look at these, it's hard to tell, I guess, from the back, but these are actually edge detection kind of going in one direction or the other. And the system has just magically made this up based on optimizing those weights. So I find this pretty astounding. And what I found even more astounding was that when I implemented a neural network to run inside that little driver program and fed it the data live from a car just sitting there doing nothing, it was actually able to drive itself around the track very successfully. So here's a video. This is the first version, driving down my hallway. And look, it actually manages to stay on the black or the dark part. And then here's a more complicated track. You can see the video coming in from the phone on the left. You can see it's deciding whether to turn left and right, and it's going forwards the whole time. Manages to go around pretty tight corners. You can even rebuild the track, and it will follow the track on the fly. So that was quite fun and quite exciting. And hopefully that's given you a flavor of how putting together the cheap commodity hardware, the really cheap commodity hardware, the open source hardware platform, and the compute power of the machine here to actually implement the neural network, I could do something pretty serious. So what's next? Well, a couple of things. So first of all, it's all very well having to have a big computer, but wouldn't it be way cooler if it could run on a Raspberry Pi? Well, this is an alpha board for Raspberry Pi, and what I've been doing for the last month or so with this, I don't get a lot of time to spend on it, is implementing the neural network on the Raspberry Pi. And in fact, if you go to the GitHub repository now, you'll see I've rewritten it in C++ instead of Java, just because Java on ARM on the Raspberry Pi is very slow. And there is a version that can actually drive the car on Raspberry Pi. Now, using that implementation, it only manages to process about 2 frames per second. This Mac is able to process about, well, an arbitrary number. The Wi-Fi network can stream about 25 frames per second from the phone, and it can handle that easily. The Raspberry Pi could only manage 2 frames a second because I haven't been using the GPU unit that's on Raspberry Pi. So I'm now working with Eben Upton from the Raspberry Pi Foundation and some other folks to actually get the linear algebra libraries that you use to implement the neural network running on the Raspberry Pi's GPU. And hopefully that'll be useful for a bunch of other projects as well as this one. But that's going to be a lot of fun. What you can see in this little tiny screenshot is the driver program actually running on a Raspberry Pi on my TV in my living room. But as I said, it doesn't quite work yet. And then the other thing is, I'd love to use all the sensors in the phone. So this phone doesn't just have a camera. It has accelerometers, which can tell what the acceleration is along 3 axes. And by summing those up, you can also tell what the velocity is. So I have this vision, because obviously the speed that you're going should be important when you're driving a car. I have this vision of the car being able to kind of coast into the corner and use its inertia to come out, which should be possible using the accelerometer. And if you look in the code, you'll see that the system now is actually grabbing those data, but I haven't yet connected them back through to the neural network. So that's what's next. And then lastly, before I take some questions, I want to show you an outtake, which is quite interesting. So here's the car driving around the same track, cornering nicely. And watch what happens here. So that's a very tight corner. Uh-oh, it's gone off the track. But it's actually managed to find another part of the track. So let me show you what's actually happened there. So I've got a few of these. It mostly does manage to stay on the track, but when it can't, it's quite interesting what happens. So you see the car here. It already knows that it needs to, or in one more frame, it knows that it needs to turn. There we go. It knows it needs to turn. But this is actually too tight a turn for the car's turning circle to make it around this corner. So it's never going to make this. This is just not going to work. It really would be better if it had stopped and reversed, but in the training data that I provided it as a driver, it had never seen such a circumstance, so that's not possible. So instead, what the neural network does is it kind of notices that there's this other thing over here that might be a good track that it could make it to, and look what it does. It steers towards that and then manages to drive along it, and this is the image that the car is seeing. So I thought that was pretty amazing, because this is nothing it had ever seen before in the training data, but yet it managed to steer itself really consistently along this path. So even when things go wrong, they can kind of go right in a way. Okay, so hopefully this whetted your appetite for a bit of hardware hacking, a bit of Heath Robinson pulling things apart and soldering them up. If you would like to learn more, then there's a blog post on my blog. The code is all open source on GitHub, and I hope you'll have fun playing with it. And we have a few minutes if you'd like to ask me any questions.
Do you have plans to make it work for a better controlled car and plans to make it work for a better controlled car and a little bit of noob on the neural nets, but then with a gradiated turning, could it have more values, or would you need a separate output node for every degree of gradation of the turn? And the same with the kind of acceleration.
Yeah, so it's a good question. So the question is, could you do kind of gradiated turning rather than, or would you need a separate output node for every degree of turn? So in actual fact, the Alvin system that I showed you did actually have gradiated turning, because it was able to turn a steering wheel to an arbitrary angle. And the way that they did it was that they had multiple output nodes for each angle, and then you can kind of see it converge and where it should be turning to. It would also be possible, I mean, you don't just get a 1 or a 0 out of these output nodes, you do get a number. It would be possible to try to propagate that back through the training system as well. So that would be a very interesting experiment to run. Actually, an aside, I managed to, this got a bit of press coverage. It was on Hacker News and Hackaday, and then I started getting folks asking me to come talk about it, which is great and a lot of fun. But I was lucky enough to be able to talk about it with one of the guys who'd actually worked on Alvin at CMU. And his initial reaction was like, wow, it's amazing to see this with high-resolution video, which was pretty funny. But it was great to talk to them and learn a bit more about their system. Any other questions?
How long did it take you to do most of that?
Good question. How long did it take me to do? I got the bulk of it working in a weekend. So I got it, the first video I showed with it driving down my corridor, that was a weekend. But getting from, and my wife was not very happy that weekend, getting from there to having it driving around the track and all the code open sourced and so on, I probably put in another, probably like a weekend's worth, a full weekend's worth of work over various evenings. So yeah, it didn't take that long, and luckily there's a lot of stuff out there to build on. The Arduino stuff's really easy to use. The Stanford machine learning course framework was pretty easy to adapt. So yeah, it wasn't so difficult. Paul?
What do you have on the intermediate board between the Arduino and the remote
So the question is, what do I have in the intermediate board? Oh, my Wi-Fi is connected to just the Android phone. I was going to show you the circuit board. Essentially, for anyone who's familiar with electronics, I have a bunch of opto-isolators. So those are little integrated circuits that can switch on and off connection when voltage is applied on the other side, but keep it electrically isolated. So you could do this without electrical isolation, but I didn't really want the junk on the radio control board that I had ripped apart and soldered, possibly breaking my my USB port on my computer. So I used opto-isolators to keep them sort of electrically separate. The circuit diagram is on the web if you go to that URL. Any other questions? Cool. Okay. Well, thank you very much.